Hi. In the previous video, we learned how to solve first order differential equation with constant coefficient and constant term. So we learned how to solve equation of the following form. And we showed that, well, let's go to definite solution. A definite solution for this equation, that it is equal to t equals ae to the power negative at plus b over a. But at the very end, I brought your attention to one detail. Look, in this case, we are dividing by a. So a must be different than 0. Now, what happens if a is equal to 0? So now we're going to consider the case of a being equal to 0. Okay, let's see first what happens to this equation. Okay, so this equation transforms into dy dt equals to b. And look, this equation is something we can again calculate, solve using simple integration, right? First, I'm going to take an integral of both sides of this equation. Okay, look, here actually those dt's are canceling each other out, so we've just got dy. So integrating, because it's like you can think about it, I always tell you to think about it as having 1 in front of dy. So in the integral of this is going to be y plus some c y. What will we have on the other side? Well, here we have just b. So it's equal to b to the power of b plus some c 2. Now, if we're going to collect both c terms, we can write it even in a nicer form, the one that is more familiar to differential equations, a plus b times t. So, okay, let me just rewrite this as 5t. Although I hope you know this really well at this moment, but look, this is a solution to a differential equation that we just had. And look, it's not a very complicated one, but there are some differences. Because look, those differences maybe are best shown if we use the classical approach. So let's find complementary function first. Okay, look, we know the complementary function y, c, is given by a to the power e negative at, right? But in our case, a is equal to 0. So what we are getting? A to the power a times e to the power of 0, which is just a. So look, actually in this case, complementary function is a constant. Now, let's go to a particular integral. Okay, so, look, in case of particular integral, we are always trying the simplest possible solution. But look, here, so previously we started with a constant solution. But look, here, the constant solution is not going to work. Why? Because a constant is not going to give you derivative equal to another constant, right? Well, we already know that, that this is the solution, but we should try a different number to actually a different expression to actually try as our trial solution. Okay, so look, in this case, our trial solution is going to be k times t, linear function. Well, the second most simple one. And look, if we have that our trial solution is y equal to k times t, then derivative is equal to just k. Right? Now, if derivative is just k, we can use this over here, and it turns out that our k is equal to b. So we get from this that particular integral in general is equal to b times t. And of course the complete solution is what you see over here, and what we were able to actually find using direct integration. Okay, now again I want to go back to the case of interpreting those two components, so complementary function and particular integral, a little bit later. Let me just tell you one tiny thing. Okay, look, actually particular integral over here as well as over here. So over here, actually it doesn't matter. The one that we have for a case with a different than 0 and with a equal to 0, their particular integral always represents the same thing. This thing is equilibrium value. And look, I just want to point this at this moment because we're going to discuss it in more detail later. And look, here we've got as equilibrium value a constant value, a given number, right? Now, over here we have a linear function of time. So in this case we've got constant equilibrium, while here we've got moving equilibrium. Equilibrium that moves with time. Okay, so now that we know how to solve a differential equation, how can we check if our solution actually works? Well, let's get to the topic of verification of that solution. Look, for now, because look, all we did now is that we had some differential equation. I showed you how to solve it. I showed you the solution. Well, I proved it to some extent, but we never actually went back and said, okay, but how do I know does it work? Okay, so we're gonna check it right now. Look, we had the definite solution. Okay, so we have differential equation dy dt plus ay equals to b. And we said the definite solution to this equation is given by y of t equals to y0 minus b over a e to the power negative at plus b over a. So, how can I check if this solution actually works? Well, we should do this, we can do this very simply. Look, what we should do is to substitute this equation over here. But is this enough? Look, in this equation, we've got not only the variable, but also the derivative of this variable. So before I can proceed to substitution and making sure that both sides of the equation are equal to each other, I need to calculate the derivative first. Okay, but look, over here, finding the derivative is super easy. Because, look, using exponential rule, all I need to do is when I differentiate, look, this is a constant number, right? It's going to stay up front. Okay, so let's maybe start with this. Now, then, when I differentiate the expression with e, the derivative of the exponent goes up front. In this case, the derivative is negative a. And now, this is a constant, so in differentiation, it's gone. Okay, and look, now we've got function, its derivative. Now we can substitute them both into the equation and make sure that the solution works. Okay, so we get so we start with the derivative. We've got that this is negative a. Oh, of course, times e to the power negative at. Yeah. So we've got negative a times y0 minus b over a times e to the power negative at. Now plus, and now we need to add. This whole thing. Okay, so I'm going to do it. I'm going to do it slowly in steps. Okay, so we've got y of 0 minus b over a, e to the power negative at plus b over a, and this should be equal to b. Okay, so what do we need to do? Look, first thing is that I would like to get rid of these brackets. So I need to multiply everything by a. If I'm going to multiply this by a, I'm going to get this. And if I'm going to multiply particular integral by a, I'm just going to have b. And now, what else can we notice? Those two expressions are identical, but they are characterized by the opposite sign. So what do we get? B is equal to b. And if b is equal to b, then of course the two sides of the equation must be, of course, the same. Okay, so let's now do an example on it. Okay, look, let's go back to the example we already solved. Okay, and let's verify that the solution that we've obtained actually works. So it is dy dt plus 2y equals 6. Okay, so let's first solve the equation. Well, we've got that y of t is equal to y0 minus b over a e to the power negative at plus b over a, which is equal to y0. We also had the initial condition here. The initial condition here was that y equals to 10, right? So let's do it right away. So b over a is 6 over 2, which is 3, initial condition is 10. 10 minus 3 gives us 7. And we've got e to the power negative at plus the negative 2t, because a is 2, and then plus b over a, again 3. Okay, now that we know the function, we know the solution, we can start verifying if the solution works. So first, I need to calculate derivative of this solution. So dy dt is equal. And again, when we differentiate exponential function, we get derivative of this expression up front. So we get that this is negative 14 e to the power negative 2t. And of course, a constant is gone in differentiation. Right? Okay. So now let's substitute what we've got. So we've got that this is negative 14e to the power negative 2t instead of derivative, plus 2 times 7e to the power negative 2t plus 3 equals to 3. And again, look, this is just 14. So we've got negative 14e to the power negative 2t times 2 times 14 plus 14e to the power negative 2t. They cancel each other out. Again, we've got 3 equals to 3, which means that the solution actually works. Okay, so look, basically this is all the necessary theory you need to know at the very beginning of our journey through the world of differential equations. In the next video, we're going to start with an economic example, economic application of differential equations that you're very familiar with, because this is going to be a market model, but for the first time, we're going to add to it dynamics, and we're going to see how market is going to equilibrium, is it going to equilibrium, or maybe what are the necessary conditions for the market to be able to get to equilibrium. Okay, thank you for your attention and see you in the next video.